has been a magnetic field exists. A magnetic field exists in a region. Here comes a particle. A magnetic field exists and there's a wire. Okay. So we haven't looked at sources of the magnetic field. Magnetic fields are produced by charge in motion. Magnetic fields are always produced by charge moving somehow. Now you could argue, well, what about quantum? You take my quantum class, we'll talk about that. But it's always related to charge, okay? So if you have a current and the charge is moving through a wire, then the charge is like telling the universe, hey, I'm in motion, I've got a magnetic field, all right? So we're gonna look at sources of the magnetic field. So on the overhead there, I have a wire that I've taped down to the little projector. And next to it is a bar magnet. So these compasses, these little compasses are little magnetic moments, which we haven't talked about yet, but they're lining up with the field of this bar magnet, okay? So they're all sort of in this direction. Now one would think, since they're compasses, they ought to line up with the Earth's magnetic field. And they will, kind of. They're really cheap, okay? And there's some material that's in the overhead. It's magnetic or currents, so it'll kind of mess up the compass alignment. And if you have a current carrying wire, let's say that a wire is carrying current into the board. If you've already had the lab, I've talked about this in lab, but this wire is carrying current into the board. You put your thumb in the direction of current flow, and your fingers give you the direction of the magnetic field. So the magnetic field is closed loops around the current carrying wire. So if I put a current through this wire that I have here, so I've just got a battery, and I drop the wire. I've got a battery, and I'll put a current through the wire, and let's see what happens. Oh, the little compasses start to react to the magnetic field. When those charges start to move, they produce a magnetic field. You can see that one that I've got sort of laying on the wire, is reacting. The others are kind of reacting. That one is dead. That one there on the left, it's moving a little bit, but not much. This is a small current. It's a weak field anyway, but we definitely see that you're getting a reaction from the current in the wire. This is the way an MRI works at a very basic level. If you've ever had an MRI, you've heard it burn, 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 burn. They're putting currents through the big loops, creating a large magnetic field. And in your body, you have magnetic moments, naturally occurring magnetic moments. So they're making the moments of your atoms line up with the field. Then they turn it off, and as they relax, they radiate, and they can take pictures of your insides. So that's the 10-second explanation of an MRI, but it's, yeah, magnetic resonance. So they really do make things resonate. They get in resonance with your magnetic moments, and as they resonate, relax, and try to line up, they radiate. So, okay. So we can calculate the magnetic field due to a current using the Biot-Savart law or Biot-Savart method. Okay. Two French physicists, natural scientists, whatever they were, that discovered this, or discovered how to calculate it. I think it was actually discovered by Ørsted. This was a scientist who was actually doing a demonstration in front of a group and he was putting currents through wires, and he had a compass nearby, and he realized that the compass was reacting to the current in the wire, so he said there must be a magnetic field due to these currents. So let's say you have a wire, it's carrying current I, okay, that's the positive direction of current flow. Like we did with the electric field, we broke it up into little pieces of charge, little segments of charge, and we looked at the electric field due to all those little segments, and we summed up over all of those. This is the same kind of idea. You break it up into little segments of current, okay? So this would be that little displacement vector ds. All right, so it follows the direction of current, the displacement vector. And if I'm up here at some point P, this is the point of interest. I want to calculate the magnetic field at that point. Then I make a position or a little position vector r hat that points at the point. This distance is r, okay, and I get a little bit of field at that point, dB, okay? Based on the direction of the current, this angle between r hat and ds and that distance. And the relationship, this is BO sub art, the relationship is dB is equal to mu naught I over 4 pi. Well, let me write it like this first. Mu naught over 4 pi times I ds cross r hat. My writing is not so good. Divided by r squared. Okay. We haven't talked about the cross product very much as far as, all the technical aspects of it, but it's basically a vector that gives you a vector that's perpendicular or normal to the plane formed by ds and r hat, and the magnitude depends on that angle between them. To calculate B, integrate, get mu naught I, this is a constant current, mu naught I over 4 pi times the integral of ds cross r hat divided by r squared. Okay, that's it. Where mu naught is equal to 4 pi times 10 to the negative 7 Tesla meter per amp. Mu naught is a fundamental constant. It's called the permeability of free space. Epsilon naught was that constant that was the permittivity of free space. And epsilon naught hangs around with the electric field and makes things work out in newtons per coulomb. Mu naught hangs out around with the magnetic field and makes things work out in Tesla. Okay? A Tesla, mu naught is a Tesla meter per amp. You get 1 over a meter here, because ds is a distance, this is a distance squared. Get an amp here, that cancels and gives you something in Tesla. Somebody in the other class asked, why write this mu naught thing? You're dividing out 4 pi, why not just 1 times 10 to the negative 7? Well, you could do that, but we'll see eventually why we keep mu naught this way. Okay, 4 pi times 10 to the negative 7. So I want to use BO sub art to calculate the field of a long straight wire. I'll just say straight wire. Magnetic field of a straight wire segment, current. Okay, it's a current carrying wire, it's straight. Okay, it's a line segment. So here I go. Well, here's a big fat wire. It's carrying current in this direction. So I'm going to put it on an x-axis. The x-axis is this way. This is the positive x-axis in that direction. And the point up here, here's the point where I'm calculating the field, and I let this distance equal A. Okay? It's actually above the center. It's a very fine wire. I'm drawing it very fat, but okay, it's from the center of the wire, right? Well, break it up into little segments of current. So here's a little current segment. I'll represent it by ds. Okay? That's a little displacement in that direction. I'm doing just what I did over here, only a little bit more carefully. Yeah, I don't like that. That's r hat. This distance is r. All right? This angle I'm calling theta. That's going to be a positive bit of angle. The origin for this x-axis is here. That's the origin. So I'm going to integrate over theta. So I'll integrate to somewhere over here, okay? Call this angle from where I start. In general, this angle's theta. Call this theta 1, and then from over here, that's theta 2, okay? Theta 1's positive, theta 2 is negative. So, gonna do this. ds is equal to dx I hat. Because I'm naming this x, and a little displacement vector that has length ds is dx, and it's in the I hat direction. Okay. ds cross r hat is equal to dx I hat cross r hat. Okay. That's going to be equal to dx times sine of pi over 2 minus theta. I'll write it that way, k hat. Because k hat, it's I hat cross r hat, that's in the k hat direction. The positive z direction, if this is positive y, positive z direction is this way. Okay, x, y, z. Because the angle between I hat and r hat is, you have to take the sine of that angle, which is sine of pi over 2 minus theta. But that's just cosine theta. So this is equal to cosine theta dx. All right? Let me continue over here. So, oh shoot, I erased it, but that's okay. Now I need r. R is equal to A over cosine theta, because r cosine theta is equal to A. I'm going to integrate over theta. That's where I'm headed. Okay. All right. X is equal to minus a tangent theta. That just comes from negative x over a is equal to tangent theta. Okay? Dx is equal to minus a secant squared theta d theta. Now I'm ready to plug all that stuff into what I wrote down before with B.O. Savart. So you get B is equal to mu naught I think there's a negative, over 4 pi times the integral from theta 1 to theta 2 of you put all this together and you get a cosine. That's what you get. All that stuff, you plug it all in and you get a cosine theta. K hat. Do the integral. There's an a here, sorry, because you get a 1 over a from making these substitutions. Okay. So this is equal to mu naught I over 4 pi a times the sine of theta 1 minus sine theta 2. Okay, that's it. So for a wire segment, if I'm integrating from here to here, you know, maybe this turns real sharply and I want to know, okay. Somehow magically I get just current in that little segment. But like we did with the electric field when we looked at the field due to a charged rod of finite length, and we let it go to an infinite length, I'm going to do the same thing here. Let theta 1 go to pi over 2, and theta 2 go to negative pi over 2. So I'm letting this means I'm letting these get longer and longer and longer. I'm looking at that limiting case where the wire gets longer and longer and longer. So this is an approximation it's a good approximation if A is very, very small compared to the length of the wire. So if you have a very long straight wire and you're close to it, okay, then B, and I'm going to write that as a magnitude I forgot K hat. Sine of pi over 2 is 1. Sine of negative pi over 2 is negative 1. This term becomes 2. And you get B is equal to mu naught I over 2 pi A. And that's it. That's the magnitude of the field due to a long, straight, current-carrying wire. You can figure out the field line's direction. You put your thumb in the direction of current, and your fingers give you the direction of the magnetic field. Let's calculate the magnitude just to get a feel for the size of this. Simple calculation. Let the current equal 100 amps. That's reasonable. Let's say we're 20 centimeters from the wire. So back to that example or the picture that I just drew. You're 20 centimeters above a wire that's long and straight. It's carrying 100 amps of current. Plug it in. B is equal to 4 pi times 10 to the negative 7 Tesla meter per amp. 100 amps divided by 2 pi times the distance from the wire in meters. Okay. All right, this is simple. 2 pi, that gives you a 2. So that's 10 times this, which is 10 to the 3. There's a 10 to the negative 7. I think this works out to be 1 times 10 to the negative 4 Tesla. Okay. The Earth's magnetic field, which is very weak, is generally a half a Tesla to a half a Tesla. This, okay, this is 1 Gauss. 10 to the negative 4 Tesla is a Gauss. The Earth's magnetic field varies from about a half a Gauss to 1 Gauss. So here's a Gauss. All right. Small field, but it's enough. Okay. You can easily detect it. I mean, over here I had nowhere near 100 amps, I assure you. I don't know what the current was, but it's way less than 100. So. Oh. All right, so I'm going to combine something that we did previously with this result. We're going to look at parallel conductors. We can do all kinds of fun stuff with these. Okay. So I'm thinking of 2 long straight wires that run parallel to one another. Here's one wire. I'll call it wire 1. It carries current I1. Here's wire 2. It carries current I2. Both of them are carrying current into the board. So I'm looking in on, they're long, straight, parallel, and they're carrying current into the board. There is, by what we just did 2 seconds ago, there is a magnetic field over here at I2 due to I1. I1 is producing a magnetic field, so this wire is immersed in the magnetic field of this wire. Here's the field direction wrapping around this way. So I'm going to call that B1. And it's in that direction. There is a magnetic field over here at wire 1 due to the current in wire 2. These field lines wrap around this way. So over here is B2. Okay. But from what we did previously, we know that if you have a current carrying wire in a magnetic field, there's a force. There's a force on that wire. I talked about the force on a current carrying wire and torque on a loop. Okay? That force is equal to I-L cross B. That's equal to, in magnitude, that's equal to ILB. In this sine theta, in this case, the angle between the current and the field is 90. Sine of 90 is 1. So for this particular example, the force is equal to ILB. Okay. I figure out the direction of that force once again with the right-hand rule. If it's cross product, this is your index finger, middle finger, thumb. These are the 2 independent variables. This is dependent. So let's see. I1 is in that direction. That's in B. So F1 is this way. I2 is in that direction. B is that way. F2 is this way. These wires attract one another. Wires that carry current in the same direction attract. They naturally try to come together. Okay? I'm going to figure out the magnitude of the forces. So F1, according to this, is equal to I1L B2. It's immersed in B2. It has a current I1. F2 is equal to I2LB1. It's immersed in B1 and has current I2. But I now have an expression for these fields. I know how to calculate the fields. Let's say that the distance between the wires, since I used A, we'll call it A, that distance between them. So B1 is equal to mu naught I1 over 2 pi A. B2 is equal to mu naught I2 over 2 pi A. When you do the substitution, you get F1 equals F2. Go over here. F1 equals F2, which equals mu naught I1 I2 over 2 pi A times L. Okay? It's a force pair. F1 is in this direction, F2 is in that direction, and they have equal magnitude. For parallel conductors, you typically see it written like this: the force per unit length is equal to mu naught I1 I2 over 2 pi A, or R, or whatever it is, the distance between them. That's it. That's on your equation sheet. I mean, we can do all kinds of fun problems with this. Let's look at this magnitude. Oh, but before I do that, I mentioned that wires that carry current in the same direction attract. That's a really good thing, because high current wires, like wires that you would run from one place to another to carry a lot of current, they're typically not one big fat wire. They're a wire that, if you take a cross section, has a lot of smaller conductors running along inside the wire. So if they all have current going in this direction, in the same direction, they're kind of compressing, they're attracting one another. If nature had it in the opposite direction, the wire would have to be held together somehow. Okay. Wires that carry current in opposite directions repel. I'll show you that quickly. Here's I1. That's current into the board. Here's I2, current out of the board. So they're carrying current in opposite directions. So B1 did not change. It's in the same direction over here. Put my thumb in the direction of I1, B1 is down. But I2, the current's now out of the board. So B2 is also down over here. Figuring out the force directions. I1 is into the board, B2 is down, F1 is this way. Okay, over here, I2 is out of the board, B1 is down, F2, my thumb was in this direction. Okay. Wires that carry current in opposite directions repel. Let's look at the magnitude of this force per unit length. Same calculation, oh, this is, some distance A. Same calculation that I had before. I'll give these some current that is reasonable. So let's let I1 equal 100 amps, I2 equals 100 amps, A, again, 20 centimeters. Makes the calculation really simple. So the force per unit length is equal to 4 pi, I'm just filling in here, 4 pi times 10 to the negative 7 Tesla meter per amp. Then I get 100 amps, 100 amps, squeeze it in over there, divided by 2 pi times 0.20 meters. Okay, this cancels. That becomes a 2. So I get 10 to the 5. So this becomes 1 times 10 to the negative 2 newtons per meter, if I did the calculation correctly. 10 millinewtons for a meter, it's not a lot of force, but it can be significant. If you're designing a high current circuit, you got wires that are carrying current in all kinds of directions, you may need to pay attention to it, okay? Usually it's such a weak force that you don't have to worry about it, but. Are there any questions on this? Okay. I'm going to stop here. We'll have the test on Friday. Next time, either on Monday or a video, I'll talk about Ampere's law. So if you'd like to read about Ampere's law, I would recommend it. Ampere's law is sort of the magnetic equivalent to Gauss's law. We do have a Gauss's law for magnetism, but to calculate the electric field, recall, we had a charge and a closed surface, and we used Gauss's law to do calculations. This is going to be the same kind of thing with Ampere's law. We have a current and a closed loop. So you have current flowing through a closed loop, and you can use that idea, which is called Ampere's law, to calculate the field based on that. So